Okay, so let's see if we can work through this one together, which again, I think most groups haven't had a chance to look at. So we've got this sample of blood that we're taking, and we're trying to figure out the red blood cell count. How many red blood cells are in, like 5 cubic centimeters of blood or whatever we take out. Okay, so the target population. Is the target population a small thing or a big thing? Forget blood example. The word population. Does it mean the small thing or the big thing? It is the big thing. What word is the small thing? Is sample. Okay, sample, small, s, small. So the sample is the small thing that actually we look at. Population is the big thing. What are we trying to get information about in this problem? Is the blood and the red blood cells in your body. So all blood in your body. Doesn't have to be exactly those words. I would say that's the target population. You're trying to get information about all blood in your body by taking a small sample of blood. Okay, the parameter, which is generally a numerical thing, it's a number. What specifically are we trying to count? Yeah, how many red blood cells do we have? So the parameter is the number of red blood cells. Okay, let's jump to part D because the sample is easier to think about than the sampling frame. So let's just ask about the sample first, and then we'll come back. So the sample is the actual things that were studied. Mm-hmm. You can, and we'll talk about the sampling methods on the next page. Okay, Melissa, please. Okay, so the sample is the actual cubic centimeters of blood that were drawn. The sample is the actual stuff that's being studied, the actual people that were studied, the actual lottery tickets that were bought, the actual students that were taking the yoga with the test, the actual blood that was drawn is called the sample. It's even called the blood sample. That's the sample. Sample. We skipped C. We're going to come back to it. So the sample is the actual stuff that is studied, small. The sampling frame is the stuff that has a chance of being studied, even though it wasn't necessarily collected. But we want to know what blood, of all the blood in your body, what blood had a chance of being, actually drawn in that syringe. So if this is going to be an accurate study, then the hope is that every drop of blood in your body has a chance of being drawn, when you're at the doctor's office. And so this is something that I don't know a whole lot about. I'm weak in terms of biology, but is it true that the blood flows everywhere? Like is that true? Like there's no blood that just like kind of hangs out in my right ear and it never circulates. It just goes everywhere, right? That way. So this actually seems like the sampling frame is all the blood that's in my body. If there's no blood that just kind of like, all right, so you have the blood drawn from your arm, and as long as every drop of blood in your body at some point is passing along this vein, it doesn't have to be there right when I get the needle out, but as long as every drop of blood moves around everywhere, circulates everywhere, then the sampling frame is all the blood in your body. And this makes this an ideal kind of study. Just like what? Yes. And that's a good thing to point out. If your study is going to be accurate, then the answer to part A, the target population, is supposed to be exactly the same as the sampling frame. You're trying to get information about all the blood in your body. We're going to take a sample, and every drop of blood in your body has a chance of being in the study. Contrast that with the spring break example, where we went and we asked 100 students, do you want to get rid of spring break to end spring semester a week earlier? You're trying to get information about all college students across the country. Did every college student across the country have a chance of being asked about their preference for spring break? The answer is no. The only people that had a chance of being asked were the ones that were at the schools that these interviewers went to. I can't imagine that every student had an opportunity to be in that study. For the lottery tickets example, we were trying to get information about every $1 lottery ticket in the state of Massachusetts. Did I go to every store in the state of Massachusetts and maybe pick one from this store and one ticket from that store? No, I went to one convenience store. It's easier for me to do that. But that's not so great because maybe the convenience store that I went to has tickets that are particularly lucky and other stores are not as lucky. And that's not so great. But it's okay to take a sample of your blood because of this biology thing where the blood circulates and every drop could be anywhere at any moment. So every part of your circulatory system has a chance of being in this particular sample. That's a good thing. That's what makes the blood test something that you can actually get reliable information from. Melissa. I'm not sure what that means. Mm-hmm. Okay, so I don't know that everybody had a chance to look at the children's study, but we had some study. We were trying to figure out if there was any relationship, any link between whether or not a baby is breastfed and their anxiety levels later on in life. That's the question. And so we'd like to get information about all children. What children had a chance of being in this study? Was it all children? I feel like it's only the children that were born in Britain between, like in that 1 week period in 1970. Did every child have a chance of being in this study? The answer is no. Only the people born in that specific country in this specific week of that specific year, and that's kind of a weakness of this particular study, right? And so if it happened that there was something else going on in Britain in that week that also related to anxiety, completely independent of whether or not a child was breastfed, well, that would kind of get in the way of what we're trying to understand here. This link would kind of become murky. So in that case, the target population, all children, would not be the same as the sampling frame, only the babies born in Britain in that week. Okay, so let's move on to E. Why would we use a survey rather than a census? Remember, a survey is where you ask a small sample. Census is where you ask everybody. Morgan? Okay, so death is a good reason we don't use a census when we do blood sample. You'd get real good information about your blood if you could take every drop of your blood and send it through the crazy machines and they can analyze the red blood cell count and have perfect information. Unfortunately, you would no longer be around to get that information. So we use a sample, a survey, instead of the census. Okay, the sampling method. Sampling method. There are 4 different sampling methods we've discussed. There are others, but we're just looking at the 4. I'll remind us, we'll go back just a few pages. The sampling method is the method that we use to describe how we selected the sample, how we chose the particular blood in this case. So where are we? Convenient sample, simple random sample, quota sample, stratified sample. What do you think when you go to the doctor's office and have this blood drawn? Which one of those sampling methods do you think is the most accurate? Simple random. If we believe that the blood circulates and we believe that any drop of blood can be anywhere at any moment in time, this is a simple random sample. And again, that's what makes blood samples reliable, is that they don't have any kind of, like the blood that's in my arm right now is pretty much the same as the blood that's in my leg at this moment. It's the same as the blood that's in my right ear. It's all the same. And so it hardly matters when I take it or from which part I take it. It's all the same. It's all mixed up. It's all random. So we'll say, where did we go here? Here. Simple random sample. Okay, and then part G, possible sources of bias or error. So what things might go wrong that would skew the results? We're trying to get an accurate red blood cell count for you the moment you're in the doctor's office. What other kinds of things might affect your red blood cell count that maybe would be kind of temporary, but maybe would skew the results? We'll go to Melissa and then Morgan. Okay. Maybe you were sick. Okay, very topical, blood doping. Okay, infection near the, what's it called? Near the draw site, that's good. Okay, I heard over here, Nicole. Inexperienced nurses, and I think maybe it was Lucas that I heard say something about, yeah, inexperienced nurses and the handling of the blood. If they make some mistakes, then that's a problem. That would throw off the results. Okay, so maybe you're taking some medicine. Isn't it true that sometimes when you're going to go have a blood test, they say make sure you don't take, sometimes you can't drink water, you can't eat food after 9 o'clock the night before, you can't take any aspirin, you can't take certain drugs because they would affect the short term, they would affect the information about your blood. So we'll talk about medicine. What's going on now about you? Okay, so inexperienced or maybe intentional, errors made on your blood. Yeah, super, Melissa. Yes, it is. I'm looking for exactly these answers or no credit. I'm just kidding. So all I'm looking for is to make sure that you guys show me that you are thinking about some of the possible problems. And so on the test, I'll give you the little paragraph about the blood sample, and I'll ask you to name 2 specific sources of error. And it could be that the two that you write down have nothing to do with the 2 that your neighbor wrote down, and they have nothing to do with anything. And that's totally fine as long as you show me that you're thinking about some of the problems that might go on behind the scenes. That's it. Okay, so again, I know that not every group had a chance to do all of these, so keep working on them after class, and I'm happy to go through some answers. Maybe we can start next class by just looking at another one. But for right now, let's move on. And we're going to jump down to the bottom of page 19. And we'll just take our quick look at the calendar here. So today we talk about something called the capture-recapture method. Again, don't forget the plan for project 1 was due last class. I've returned the plans for everybody that turned them in last class, and that's great. But if you didn't get it into me last class, then hopefully it's in the folder now. And if it's not in the folder now, get it to me Tuesday. The point is that I want you to not wait until the day before the project is due to decide to do a project, and then turns off you're way off base, but I don't have a chance to talk to you about that before you spend your time doing the project. So the project is due October 30th. What is that? A week from this Tuesday, right? It's coming. So 12 days from now, that project number 1 is due, okay? Again, a bunch of people are doing the conduct your own election, which is fine. If you want, I'm happy to distribute ballots in this class, and we can spend a few minutes doing election stuff here. So let me know if that's something I can do for you. You print out the ballots, and I'll give you just a minute in class time to get answers. All right, one last thing on the calendar. So I will just highlight that right now we're right in the middle of the information for test number 2. I think I've highlighted 8 days. Yes, so test number 2 is on 8 days of material, same as test number 1. Right now we are on day 4. So at the end of today, we're right halfway in the middle of the test number 2 material, okay? Second test is coming up on November 13th. All right, so here on the bottom of page 19, we're going to talk about this idea called the capture-recapture method. And the idea is this. Oftentimes there are populations that are hard to measure, like a population of elephants in like a huge forest type thing. It's going to be difficult to actually get, to take a census of these elephants, because you can't ask all the elephants to hang out in line and count them one at a time as they go by. And so we're going to have to try to do something to estimate the population, which doesn't involve a census. So we're going to do kind of a survey thing that we've talked about. So we're going to jump down here to 4, and then we'll go up and take a look at the formulas that's right up above. So we'll start with 4 and Lucas. Okay, So let's understand the process here. There's this big field. It's way further than the eye can see. We go out in this field and we capture 20 elephants. We don't harm them. We're just going to tag them. And then we're going to release them back into the wild. And so some of the elephants in the wild are going to be tagged. 20 of them are going to have these tags on them, right? But there's a lot of elephants out there that we didn't capture, that we haven't seen before, that don't have tags. And so we let these elephants all kind of mingle together and get mixed up. And then a little while later, we go back out and we recapture some elephants. Now we're going to capture 30 elephants this time. It's okay that it's a little different than the first number. And some of those 30 elephants had tags on them because they happened to have been captured the first time as well. All right? So it happens in this case that out of the 30 elephants that we grabbed the second time on the recapture, 2 of them already had the tags on them. 2 of them were marked already. And what we're going to try to do is use just that information, the capture and then the recapture, to try to estimate the size of the population. So here's how it works. Suppose that, so I'm going to write down, what am I going to write down here? We're going to write down a fraction. The fraction that we're going to write down is going to have the number of tagged elephants on the top divided by the total on the bottom. And in fact, I'm going to write that fraction exactly the same over here. It'll have different numbers, but the units are going to be the same. So let's look at the recapture part first. This data right here. How many elephants were tagged on the recapture? How many elephants already had tags on them? 2. There were 2 tagged out of how many elephants? 30. Everyone buy it? That's the recapture number. Out of the 30 elephants we captured, 2 of them already had tags. Now let's think about the entire elephant population, most of whom I have never seen. How many elephants in total have tags on them? We know that there are 20 elephants out there that have tags on them, right? That's how many have tags. Out of the total elephant population, which I don't know, but I can call X. Melissa. No, the 2 that we saw the second time were in the 20. Yeah, so it's the same 2 we've already seen. So here's the main idea behind the capture-recapture method, is that these 2 fractions are going to be about equal to each other, we hope. Let's see if we buy it. Again, we randomly grabbed 30 elephants the second time, and it happened that 2 out of those 30 elephants were tagged. Is it reasonable that perhaps the entire elephant population, 2 out of every 30 are tagged? Roughly. It's not going to be perfect, but I grabbed 30 elephants, 2 of them were tagged, maybe 2 out of every 30 elephants are tagged. And that's why it's okay to put that purple squiggly in between. Morgan. Great question. Great question. What would your guess be about the size of the population if when you go out there, you capture 20 elephants and you tag them all, then you go out and you capture 30 elephants and you don't see a single elephant you've seen before? What do you think is true about that elephant population? It's probably really big, right? And that's an okay conclusion to make. Maybe it means we need to go tag some more elephants. We got to try to find some that we've seen already so we can do this proportion thing. But it's a great question. Okay, so you guys know how to solve. I'll write this maybe in more familiar looking things without all the words in it, but 2 over 30 equals 20 over x. You guys spent some time in an algebra class in your past solving equations like that. It's called a proportion. So I don't know how you guys solved it. Probably depends on the phrase your teacher used, but maybe cross multiply. Is that something we've heard before? So if we multiply these 2 things and multiply these 2 things, so 2 times x equals 20 times 30. So that's called cross multiply. If you had Sandy, raise your hand if you had Sandy for Math 105. Right, so a few of us. So I don't think she uses the phrase cross multiply. She says something like multiply both sides by both denominators. Does that sound familiar? And so for the folks that have seen it that way before, I'll write it again. What we do is we multiply both sides by both denominators. The denominators are 30 and x. But I can't just multiply one side of an equation by that. I better multiply the other side. And the real nice thing that happens here is that 30 on the top here and this 30 on the bottom cancel. And what's left? 2x, which is exactly what we have here. And over here, what cancels on the right? X cancels with the x, and what's left is 20 times 30, right? So there's a good reason that cross multiply works. I think there is a problem when a lot of folks come out of an algebra class with just this idea of, okay, fraction equals fraction, you cross multiply, but no idea why. You know, it's just like this gift handed down. Oh, cross multiply, it works. Well, it's easy. Multiply both sides by the right thing. Haley? Yeah, and so are you using, what are you using? So yes. Yeah. But don't get confused when you're doing other actions. Yeah, I think that's a good philosophy that she's got there. It's a good reason to yeah. So Haley's got our answer for us. She says that the answer is really just, well, okay, so 20 times 30 is easy enough to do, but I'm just going to leave it as a number there. And then Haley, what did you say to do? Divide by 2. Everybody buy that to solve for x. So the answer in this case is what, 600 over 2, which is 300. And I like that Haley gave us that 20 times 30 over 2, because I think I can keep this on the screen. If you take a look right above this problem that we did, oh, I don't think I can keep it on the screen actually, so we'll let people copy if they need to, and then we'll just take a look right up above. Where is it? Use proportions. Oh, you know what? I actually used to include this, but then I decided I didn't like it, so I took it away. But Haley likes it, so we'll put it back. So I think that Haley is basically giving us a formula here that says that the total population, there's that word again, is in theory, so you multiply the number of tagged animals, that's the 20, number of tagged, times 30 was the second number that we captured, and divide by, why was it 2? That was the number in the recapture that were tagged. So recaptured and tagged. If you take a moment later on to look at these letters here, I think the formula is something like this, N1 times N2 divided by K. It's easier with the letters, but you got to know what all the letters stand for. So if you like the formula and you feel like you can figure out that formula, you know, like on a test, then just use that formula every time you see these problems. But for me, I can never remember that formula, so I just write my 2 fractions every time. And if I write my units, I'll put the numbers in the right spots. Okay, so that is that. So here's what we're going to do. We're going to see if this thing actually works. So what I've got here is a population of elephants. Nobody except for me knows how many elephants are in this little bin here. So here's what we're going to do. What do we do first? We capture some. All right, Laura, can you just reach in there, grab a handful of beads? Super, that's good. Just count those for us. All right, so Laura is counting. We have 4 different numbers that have to go into our fractions here. Which is the one that Laura is counting right now? This is the captured, and where is it? Is it the 2, the 30, the 20, or the x? It's the 20. It's the first number that are captured. Laura, do you have a number for us? 15. Okay, so we'll do this on the next page here. Let's see, okay, so equals. All right, so Laura has captured 15, and that means that what we're supposed to do is tag those 15, and we're going to tag these 15 elements by making them red. Yes. It's always X right there because that's the total population you're after. All right, can you guys count out 15 reds for me, please? Thank you. So we've got 15 tagged, and the total population I don't know. I'm going to write the same words over here, tagged and population down here. I guess actually we've been calling it total, haven't we? I'll be consistent. Okay, we have 15. Okay, currently I have a bunch of the white elephants, but Laura has taken 15 of them out of circulation. What are we about to do? We're going to put them back in, but we got to make sure we know which ones they are, so we make them red. So put those 15 reds in here. Thank you. Okay, we've just done the capture. 15 out of I don't know how many are tagged. What do we do now? Shake it up. Before we recapture, and this is important, isn't it? If all the red ones are right here on the top, and I just reach in and grab, I'm going to get too many reds, right? And you notice with the elephant example, there was this little phrase there. After a while, we go back out and we recapture. You got to let those elephants kind of mingle and merge and all that stuff, because otherwise you're just grabbing the ones that are right there, and too many of them will be tagged. Okay, so this thing is all mixed up now, and then we're going to recapture. So what we're going to do is ask you guys to just reach in here. Each of you will just take out one, but do it without looking, okay? So pass it around, take one out, and we'll just keep quickly sending it all around. And you guys actually can tell me what number is going to go in one of these spots. I don't know how many are going to be tagged, because we're going to look at them together in just a minute. But can you tell me how many we're about to pull out? What do you need to count? The class. I'm not taking one.
Just one, right?
Just one. Yeah, don't look.
She said more than one.
Oh, it's fine. All right. All right, I got one vote for 18. Can somebody else count? 16. I do, but not yet. 13. I got another vote for 18, but it was the same person. Can somebody else count? How many people in the room? Don't count me. I have 16, 17, and 18. All right, 16 has taken himself off the table. I have 18s, I have a bunch of 18s, 17 and a 19. 18? Okay, all right. Okay, so not counting me, there are 18. Where does the 18 go? It's the total. We have a total number of elephants right now. 18 of them have been recaptured. And now some of them are red. So what I'd like you to do is look at your bead. If you have a red bead, stand up. Where are the beads? The beads are over here. Oh, you didn't take one? Yeah. Does nobody have a red bead?
I just asked for
Wait. 5 and 4. This doesn't make sense. There are less than 15 reds in here. Some of you have red beads. Okay, so all the red beads are right over there. How many are there? 4. 4 people at that table. Please stand up. All right. Patty tried to mess up our experiment, but I think we're okay. So we need to make an adjustment. So first of all, how many were tagged on the recapture? It was 4. We saw that. But a number in here is not accurate anymore because Patty grabbed more than one. So which number is not accurate? The total. That 18 is no good. We need you guys to count how many beads are on that table. You really, all those that are on the table, yeah, like, yeah, how many did Patty grab, I guess is the question. Yeah. Yeah, she grabbed a bunch. Wow. How many? Okay. All right, and does that count the 3 people? So does that count you 3 or no? Okay, so there were 27 more. Everybody grabbed one, and Patty happened to grab 28, which is 27 more than she meant to. So used to be 18, plus an additional 27 that Patty grabbed, so we have, what, 45. 45. Okay, you guys have your proportion. Go ahead and solve this equation somehow. Yeah, we can get a decimal. How much? 1172012October18. Okay. All right, so that 168.75, it's okay that it's a decimal. I know we can't have fractions of elephants, but we're doing a math thing, trying to apply it to real world. So maybe 160, it's just an estimate anyway. But what is that an estimate of? The population of elephants, which in this problem was the number of white beads that I started with before we started taking them out, okay? Now, I told you that I counted these beforehand. What would you like to know? How many beads were there? All right, our estimate is 168.75. I'm telling you how many beads were in there before we did anything. Okay, all right, Mariah? 146. So this is the actual answer. There's 146 beads in this case. So how do you feel about our estimate of 168? It's not bad. It's off. It's going to be off. But it's not a bad estimate. If we were feeling so inclined, we could maybe get a percent error. You know, by how much were we off? So we talked about percent stuff before. How would I find out how bad this error is? What should I do with these two numbers? All right, so we are going to divide by something. What goes on the top? Yeah, that's actually not a bad thing to do. I don't know that we used this formula when we did it, but you take this number and you divide it by the right number. Remember the, so can you look at that and tell me what percentage we were off by? I don't even know if you guys can read it in the back, but it says 1.15. It's 15%. Yeah, ignoring the 1 in the front, which is the 100%, we were off by about 15%. For us, I'll do it on the other calculator because it's a little bigger. For us, I think what we did when we did percentages way back when was we subtracted these numbers. So you would do, here I'll write it with the parentheses, 168.75 minus the 146. You guys remember doing like the actual amount minus the final amount, and then divide by the right number, the original, and there's your 15%. Melissa. Okay, so maybe some of the tagging procedures have errors embedded in them. Yeah, right. Yeah, and yeah, so our experiment was really controlled, but elephants migrate and they pass away and new ones are born. And so, yeah, it's not even a constant number we're trying to estimate. So of course, it's going to be an estimate and it's okay. So I think 15% is an acceptable error. All right, what you guys are going to do is write down here this capture recapture method example about caribou. So give it a shot. Yeah, let's get those beads back.